Good morning, students. In this lecture, we are going to learn about a software design, how to design a software, and what are the characteristics for a good software design. And all those are going to be discussed in brief in this lecture today. First of all, let us see what is the characteristics that are required for a good software design. The activities that are carried out during the design phase transforms the SRS document into the design document. There are some characteristics to say that it is a good software design. Correctness. A good software design should first of all be correct. That is, it should be correctly implementing all the functionalities of a system. Understandability. A good design should be easily understandable. Unless a design solution is easily understandable, it would be difficult for the user to implement and maintain it. Efficiency. A good design solution should be adequately address the resource time and cost optimization issues, which means that how much amount of budget is required, what are the resources that are required, and all should be estimated efficiently. Maintainability. A good design should be easy to change. This is an important requirement because whenever the changes are occurred or the changes keeps on occurring, it should have a capacity to emit those mistakes and maintain the code efficiently. The design solution should have the following characteristics that are to be easily understandable. It should assign consistent and meaningful names to the various design components. It should make use of principles of decomposition and abstraction in a good measures to simplify the design. A design solution should be modular and layered to be understandable. Structured design. A structured design is a conceptualization of problems into several well-organized elements of solution. The benefit of structured design is that it gives better understanding on how the problem is to be solved. Since it follows a divide and conquer principle, each layer of a module can be solved separately until a large problem is solved. The small pieces of problem are solved by means of solution modules. Structured module emphasizes that these modules are well organized in order to achieve precise solution. These modules are arranged in a hierarchy. They communicate with each other. A good structured design always follows some rules for communication among multiple modules. The communication modules are cohesion and coupling. A good software design should always have high cohesion and low coupling arrangements. Modularity. A modular design is an effective decomposition of a problem. It is a basic characteristic of any good design solution. A modular design, in simple words, implies that the problem has been decomposed into a set of modules that have only limited interactions with each other. Decomposition of a problem into different modules facilitates taking the advantage of the divide and conquer principle. If different modules have either no interactions or little interactions with each other, then each module can be understood separately. The next one will be the layered design. A layered design is one in which when the call relations among different modules are represented graphically, it would result in a tree-like diagram with a clear layering. In layered design solution, the modules are arranged in a hierarchy of layers. The module should also invoke functions to the modules, the layer immediately below it. A layered design can make the design solution easily understandable since to understand the working of a module, one would at best have to understand how immediately a lower module works without having to worry about the functioning of upper layer module, which means that the function of the modules in this layer design are not dependent on each other. Each layer is independent of its own functionality. A design solution is said to be highly modular if the different modules in the solution have high cohesion and their inter-module couplings are low. Coupling. Coupling is a measure of degree of interdependence between the modules. A good software will always have low coupling. Types of coupling. Data coupling. If the dependency between the modules is based on the fact that they communicate by passing only data, then the modules are said to be data coupled. If the data coupling components are independent to each other, then the communicating through data module communication does not contain any tramp data, which is, for example, it is customer billing system. Stamp coupling. In stamp coupling, the complex and the complete data structure is passed from one module to another module. Therefore, it involves ramp data. It may be necessary due to efficiency factors. This choice by the insightful designer but not a lazy programmer. Control coupling. If the modules communicate by passing control information, then they are said to be control coupled. It can be bad if the parameters indicate the information that they are said to be control coupled. It can be bad if the parameters completely have a different behavior, and good if the parameters allow factoring and reuse of functionality. External coupling. In external coupling, the modules depend upon other modules, external of the software being developed or a particular type of hardware. For example, if we consider a protocol or an external file or a device format, etc. Common coupling. The modules have shared data such as global data structures. The changes in the global data mean tracking data to all the modules which access the data to evaluate the effect of change. So it has got some disadvantages like difficulty in reusing modules, reduced ability to control data, access, reused maintainability. The next one will be the content coupling. In a content coupling, one module can modify the data to another module or control flow is passed from one module to another module. This is the worst form of coupling which should be avoided. Now let us see about the cohesion. Cohesion is a measure of degree in which the elements of the modules are functionally related. It is the degree to which all the elements direct towards performing a single task are contained in the component. Basically, cohesion is the internal glue that keeps the modules together. A good software design will have always high cohesion. Now let us discuss the types of cohesion. Functional cohesion. Every essential element for a single component is contained in the component. A functional cohesion performs the task and functions. It is an ideal solution. Sequential cohesion. An element outputs some data that becomes the input for another element. That is, the data flow between the parts occurs naturally in functional programming languages. Communicational cohesion. Two elements operate on the same input data or contribute towards the same output data. For example, update record in a database and send it to the printer. In this, communication between the printer and the modules are performed. Procedural cohesion. Elements of procedural cohesion ensure the order of execution. Actions are still weakly connected and unlikely to be reusable. For example, calculating a student GPA, printing a student record, calculating the cumulative of GPA, and print the cumulative GPA. Temporal cohesion. The elements are related by their timing involve a module connected with a temporal cohesion. All the tasks must be executed in the same time span. This cohesion contains the code for initialization of all parts of the system. A lots of different activities occur at init time, that is initialization time. Logical cohesion. The elements are logically related and not functionally. The component reads the input from the tape or disk or from any other network. All the code for these functions is in the same component. Operations are related, but the functions are significantly different. Coincidental cohesion. The elements are not related, but the elements have no conceptual relation other than locations in source code. It is accidental and is the worst form of cohesion. Example, printing the next line and reversing the characters of a string in a single component. Now, let us see about the functional independence. A module that is highly cohesive and has low coupling nature with other modules is said to be functionally independent of other modules. Functional independence is a key to any good design, primarily due to the following advantages it offers. First one is error isolation. Whenever an error exists in a module, functional independence reduces the chance of error propagating to the other modules. Scope of reuse. Reuse of a module for the development of another application becomes easier, and functionally independent module can therefore be easily taken out and reused in a different program. Understandability. When modules are functionally independent, complexity of a design is greatly reduced. This is because of the fact that the different modules can be understood in isolation, which means separately. Since the modules are independent of each other and each other design as well, we need not list out any other or any leave an assignment to the reader to identify them. Now will discuss about the function-oriented design. In function-oriented design, the system is comprised of many smaller subsystems known as functions. These functions are capable of performing significant tasks in the system. The system is considered as top view of all the functions. Function-oriented design inherits some properties of structured design where the divide and conquer methodology is used. This design mechanism divides the whole system into smaller functions first, which provides a means of abstraction by concealing the information and their operation. These functional modules can share information among themselves by means of information passing and using information available globally. Another characteristics of functions is that when a program calls the functions, the function changes the state of the program, which sometimes is not acceptable by the other modules. Function-oriented design works well with the system that does not matter the program or function work on input rather than on a state. Object-oriented design. Object-oriented design works around the entities and the other characteristics instead of functions involved in the software system. This design strategy focuses on entities and its characteristics. The whole concept of the software solution revolves around these entities. The first one is object. All the entities involved in the solution design are known as objects. For example, a person, banks, companies, and customers are tested as objects. Every identity has some attributes associated with it in some methods to perform the attributes. Classes. A class is a generalized description of an object. An object is an instance of a class. A class identifies first all the attributes which an object can have the methods which defines the functionality of the object. The next one will be encapsulation. In object-oriented design, the attributes and methods are bundled together, which is called encapsulation. Encapsulation not only bundles the important information of an object together, but also restricts the access of the data and the methods for some outside world. This is called information hiding. Inheritance. Inheritance allows the similar classes to stack up in hierarchical manner where the lower or subclasses can import, implement and reuse the allowed variables and methods from their immediate superclasses. This property of OOD is known as inheritance. This makes it easier to define specific class and create a generalized class from specific ones. Polymorphism in object-oriented design language provides a mechanism where the methods performing similar tasks but vary in arguments can be assigned same name, which means the task may be vary in arguments, but the name that we assign will be the same. This is called polymorphism, which allows a single interface performing tasks for different types. Depending upon the function is invoked, the respective portion of the code gets executed. Now let us see about the function-oriented software design. What are the types and methodologies that are involved in it? In software analysis, in software methodology, there are two distinct activities, that is structured analysis and structured design. During structured analysis, the SRS document is transformed into data flow diagrams, but whereas in structured design, the DFD model is transformed into a structured chart. Here is an example or a diagrammatic representation for this. That's all for today's class. Thank you.